Hello everyone, in this video we're going to talk about first order systems. But before we talk about first order system, let's review some underlying concept. The first one is the steady state versus the transient response. So in steady state response, we are looking at the behavior of the system after the time approaches infinity or after a very long time. Basically, any transient effects have dissipated and our system has fully adjusted to the input. If you're going to look at the first example here, you can see we have some transient response at the very beginning, and after a very long time, we are going to reach this plateau. We call this the steady state. Because after any excitation, the system needs time to reach its final value. Here, we can see a second order system, but the concept of a steady state still remains, and this line you can see after a very long time we'll get to the steady state part, and then the initial part would be the transient response. Depending on the problem and application, we might be interested in the transient or the steady state response of our system. And the last example here, I'm showing you the behavior of different systems that are going to have vastly different transient response, but interestingly the steady state response would be the same. You're going to reach that value of 1. Again, depending on the application, you might care how fast you're reaching the steady state response. If you're putting your car at a specific speed in the cruise control, you care whether you get there in 5 seconds or 2 seconds or 1 second. So the transient response is important. But for us, now we are going to focus on the steady state response. If you look at the inputs, there are 3 main common inputs in system dynamics: impulse, step, and ramp. So the mathematical equation for impulse is that at time 0 we have infinity, and at any other time would be 0, which means that we have a sharp excitation and then goes to nothing. The Laplace domain, we just use 1, and an everyday example of that, you can think of it as striking a bell with a hammer. You have a very sharp excitation and it goes away. We have removed it. The contact was a fraction of a second. What is the steady state response? 0, because that effect after a long time would go away. And the transient response would be very interesting for the case of impulse. The other common input would be a step. As the name suggests, we step up our input. So it's 1 after our time begins, after 0, and it stays at 1, or any other constant for that matter. And the Laplace domain would be 1 over s or c over s, depending on our magnitude of our step function. And a good example for it would be the thermostat adjustment. Let's think of it that the thermostat is set at 70 Fahrenheit, and then you want to bump it up or step it up to 75. So we have used the step function to increase the temperature. And the steady state would be the value of the constant value that we set, 75. There would be some transient response because it's not going to reach that immediately. But depending on the nature of our system, that transient response could be short, could be long, it could be an overshoot, it could be an undershoot, and so forth. And the last input that is very common is the ramp. Basically, the function here is a linear function, and this is function t, and the corresponding Laplace would be 1 over s squared. It doesn't have to be linear. We could have other function as well, and you can think of it as an acceleration of a car. Because the system is unstable, we do not have a steady state response. The steady state response cannot really be defined for a ramp function, because our output grows indefinitely and it would never stop. It just grows. Let's look at this exercise to see if we have understood different inputs. Here in this plot that you see on the right, we have 3 inputs, but we just label them first input, second input, and third input. We are going to identify which one is which. I'm going to start with the first input, the blue line. If you look at it, we have an excitation and it just dies out, reaches 0, a steady state. That's a perfect example of an impulse input. The second one either steps up, so that's a step. Still we have a steady state response, and the third one would be ramp, because it grows indefinitely and we don't have any steady state. If you look at on the left, here we see the Simulink version of this. So we have our inputs. The first one is impulse, the second one is step, and the third one is ramp. We have our transfer functions. These boxes are transfer function, and then we can get our output scope. So I have plotted this by just looking at this scope. One thing that you need to pay attention is that MATLAB does not distinguish between impulse and step. We use the same function for both. But manually we are applying S in the numerator of our transfer function whenever we are talking about impulse, because you're just going to remove the effect of that step and then have it as an impulse. Now we are ready to talk about first order system. We are not very innovative with our naming. First order system, which means that in our differential equation, the highest order is the first order. We have the first derivative of our function. And then we have a mathematical representation of this first order system as well. You can see you just have a linear component. And usually the behavior of the first order system is exponential, which is a steady state value if it is stable. It is a steady state value, and then we have some exponential function reaching that steady state value. In this representation, A is a constant and tau would be time constant. So this time constant is very important for us. It tells us how fast we reach the steady state response. We talked about it, that we might be interested in the transient response, in the speed of our system, and that would be the indicative. If tau is very small, that means that our system is very fast. If tau is very large, that means that our system is slow. It tells us about how long it takes to reach that steady state response. To find this tau, we can rearrange our transfer function to have this form. One thing that we need to pay attention is this tau s plus 1. What if it's not 1? We just divide the numerator and denominator by that value. Let's say we have 10s plus 5. If I want to find the time constant, I know this one has to be 1, so I divide everything by 5. So I have 2s plus 1. Then I know this would be my time constant, 2 seconds, which might be short or long depending on your application.